are going to discuss about the structure of materials. If you remember, in our last lecture we have already discussed about the atomic bonding and the atomic structure of different materials. So, in this particular lecture we will only focus on the structure of materials. So, first let us know that what is structure. So, structure is related to the arrangement of the components of a material, that means it is the skeleton of any kind of material. It could be on any length scale like atomic, nano, micro or maybe the macro, and all length scales matter for structure. Structure generally we are dividing into two levels. First is called the atomic level and second one is called the microscopic level. Atomic level, which will give us the different arrangement of atoms in different ways, and microscopic level, that means it will give you the small grain of materials that can be identified by the microscopy, either maybe it is optical microscopy or maybe scanning electron microscopy or maybe the transmission electron microscopy. So, generally there are two types of structure. First one is called the crystal structure and second one is called the electromagnetic structure. So, if we do the classification of the crystal structure, so as I told already, the crystal structure it will be divided into three parts. One is called the metallic crystal structure, then ceramic crystal structure, and last one is the polymer structure. So, if we see the metallic crystal structure, so we can find three types of structure. One is called the BCC or maybe the body centered cubic, then face centered cubic or maybe the FCC, and last one is the hexagonal close packed, or generally we are calling it as a HCP structure. When you are talking about the ceramic crystal structure, generally it is AX type, AMXP type, AMBXNP type, and when we are talking about the polymer structure, so generally polymer crystallinity and polymer crystal. So, now first let us discuss about the metallic crystal structure. So, generally the metallic crystal structure have metallic atomic bonding. So, that is why it is known as the metallic crystal structure. So, it is non-directional in nature, it tends to be very densely or maybe the closely packed, the gap in between the atoms is very less. For metals, generally using the hard sphere model for the crystal structure, each sphere represents an iron core. So, what is the reason for the dense packing? So, generally one element is present, so all atomic radius are the same. Metallic bonding is not directional, and last one is that nearest neighbor distances tends to be small in order to lower the energy bond. So, there are mainly three principal crystal structure found in the common metals, more or less 90% of metals. One is called the body centered cubic, then face centered cubic, and the hexagonal close packed. So, now let us discuss about the some common terminology that generally which we are using for determining the crystal structure. So, first is called the coordination number, or maybe in short we are calling it as a CN. So, what is that? It is the number of nearest neighbor to a particular atom in the crystals. So, nearest neighboring, how many partners or maybe atoms are present over there, that is known as the coordination number. Next is known as the atomic packing factor. This is very important one. So, it is also called as a packing efficiency also. So, it is the ratio of volume of atoms in the unit cell and volume of the unit cell. So, generally we are giving atomic packing factor is also known as the, in short terms, is called the APF. So, what is APF? Volume of atoms in a unit cell divided by total unit cell volume. Generally it indicates how closely atoms are packed in a unit cell. Next we are going to know another term, that is called the linear density. So, it is the number of atoms per unit length along a particular directions. So, linear density is generally number of atoms in the direction vector by length of the direction vector. So, in this case you see, so when we are talking about, we are having A and C point, and then what is the length of the direction vector? It is root over 2a, because it is the cubic structure. So, all the sides are A. So, automatically this A to C is known as the root over 2A. Now, what are the number of atoms over there? If you see it, that it is half of that one, then one single and another half. So, total number of atoms is 2. So, what is the linear density over here? That is 2 by root over 2A. So, another important term is called the planar density. So, generally planar density, sometimes it is called as a PD. So, it refers to density of atomic packing on a particular plane. So, generally planar density, number of atoms on a plane by area of a plane. So, when we are talking about a 110 plane, so generally if you see, that is also a cubic structure. So, here 110 plane is nothing but the plane is consist of A, C, F and D. So, if any cube, just we make it a cross section and just corner to corner. So, in this particular case, what are the number of atoms on a plane? It is 1 by 4 into 4 plus half into 2. So, the total number of atoms present are 2, because these 4. So, 1 by 4 of that part. So, 1 by 4 into 4, and this one B point is half and E point is the half one. So, total number of atoms is 2. And what is the area of plane? Root over 2A, because this is A to C is root over A to C is root over 2A into the height, that means A. So, root over 2A square. So, the planar density along the plane 110 is 2 by root over 2A square. Now, if we talk about the BCC structure, so here the number of atoms on a plane 110 is 1 by 4 into 4, because 1, 2, 3, 4, A prime, B prime, E prime, D prime. So, 1 by 4 into 4 plus 1 is into the middle. So, that is the C prime. So, here is also the number of atoms is 2. Area of plane, it should be root over 2A into A, because A prime to B prime is also here root over 2A. Now, what is the planar density? 110 plane, it is 2 by root over 2A square. Now, we are going to discuss about the density computations. So, crystal structure of metallic solid permits the computations of its theoretical density through these relationships, which is nothing but the rho is equal to Na by Vc Na. What is capital N over here? N is nothing but the number of atoms associated with each unit cell. What is A? A is the atomic weight. What is Vc? That is volume of unit cell. What is Na? That is nothing but the Avogadro's number, that is 6.023 into 10 to the power 23 atoms per mole. Now, we are going to discuss about the body centered cubic crystal structure. So, in these particular crystal structures, atoms are located at all 8 corners. So, from this figure, this B figure, you can see that atoms are located all the 8 corners over there, and a single atom at the cube center. So, this one. So, total number of atoms per unit cell is equal to 2, already we have gone through in our last slides, because the center atom not shared, that is 1 into 1, that is 1, and 8 corners atom shared by the 8 cells, that is 8 into 1 by 8, that is 1. So, 1 plus 1 is equal to 2. What is the atomic packing factor over there? So, generally atomic packing factor is 0.68. How we are calculating this one? If we clearly see this image, so you can find that from F to B, so automatically there is one half atom, one full atom and another half atom. So, if I take the radius of the atom is r, so total distance is 4r, which is nothing but the root over 3a, because if in a cubic systems, if all the sides are a, so automatically F to B will be root over 3a. So, root over 3a is equal to 4r. So, now what is the total volume of the atoms? That is 2 into 4 by 3 pi r cube is equal to 2 into 4 by 3 pi, and if I put the value of r over here, which is nothing but the root over 3 by 4 a to the power cube. So, volume, and here also the volume of unit cell is A cube. So, now what is the atomic packing factor? Because atomic packing factor we know total volume of the atoms in a unit cell by the volume of the unit cell. So, it should be this divided by this. So, what we are getting actually finally root over 3 by 8 pi, which is nothing but the 0.068. What is the coordination number over here? That is 8. Hard spheres generally tough along cube diagonal. So, cube edge length, if I want to calculate the A, so generally the A value is equal to 4 r by root over 3. So, same we are getting from these particular dimensions. So, generally it can be found in chromium, iron or tungsten. Now, we are going to discuss about the face centered cubic crystal structure, or maybe in short generally we are calling it as a FCC structure. So, atom touch each other along face diagonals. Here the number of atoms per unit cell n is equal to 4. How we are getting this one? So, if you see this B figure over here, so you can see all the corners we are having 1 atoms, then all the faces we are having 1 atoms. So, 6 face atoms shared by the 2 cells, that is why 6 into 1 by 2 is equal to 3, and 8 corner atoms shared by the 8 cells, 8 into 1 by 8 is equal to 1. So, 3 plus 1 is equal to 4. So, total number of atoms per unit cell is 4. So, now what is the atomic packing factor over there? So, if we see, then we are doing the same thing. Now, we are just going to take the distance from this point to this point. So, what is that? Same thing, it is half, then full, and then half. So, r, then 2r and r. So, total it is 4r. So, 4r is equal to root over 2a, because this is the root over 2a. So, now how it is possible? If all the sides dimensions are a and all are perpendicular to each other for a cubic system, so automatically this will be root over 2a. So, root over 2a is equal to 4r. So, now total volumes of atoms is equal to 4 into 4 by 3 pi r cube, which is nothing but the 4 into 4 by 3 pi, and just we are replacing the r value over there, which is nothing but root over 2 by 4 r. A value just we are putting the r value root over 2 a by the 4. So, we are putting over here and then whole cube, and here the volume of the unit cell is a cube. So, what is the atomic packing factor over here? Same thing, total volume of atoms in a unit cell by volume of unit cell, which is nothing but root over 2 by 6 pi, which is nothing but the 0.74, whatever we have written over here. So, what is the coordination number over here? The coordination number is 12. Hard spheres touch along diagonal, the cube edge length is a is equal to 2r root over 2. Then generally it can be, FCC structure can be found in copper, aluminum, silver, gold, etc. Now, we are going to discuss about the hexagonal close packed structure. So, generally 6 atoms form regular hexagon surrounding 1 atom in center, you can see from this particular image. Unit cell has 2 lattice parameters here, one is called the A, another one is the C. So, A is the distance between A to B, and from B to A the distance is C. What is the number of atoms per unit cell? N is equal to 6. How we are getting it? 3 mid plane atoms not shared, so it is directly 3 into 1 is equal to 3. 12 hexagonal corners atoms shared by the 6 cells, so 12 into 1 by 6, that is 2, and then 2 top bottom plane center atoms shared by the 2 cells, so that is why 2 into half is equal to 1. So, 3 plus 2 plus 1, so that means total 6. Now, how we are going to calculate the atomic packing factor over there? So, for this you have to see this picture. In this picture you can find that we have gone through these triangle shapes J, K and L. So, the triangle JKL total volume of atoms, what is that? 6 into 4 by 3 pi r cube, which is 2 into 4 by 3 pi into a by 2 whole cube. So, what is the area of this JKL triangle, it is root over 3 by 4 a square. What is the volume of that HCP? Area of 6 triangles into C. C means this one. Height of HCP, which is nothing but the 6 into root over 3 by 4 a square C is equal to 3 root over 3 by 2 a square C. So, what is the APF value over there? Total volume of atoms in HCP by volume of HCP, which is nothing but the 2 pi by 3 root over 3 into 1.633, which is nothing but 0.74 over there. What is the coordination number? So, here the coordination number is 12. The cube edge length A is equal to generally 2R, found in generally cadmium, magnesium, zinc, titanium. Here coordination number and atomic packing factor is same as FCC. Now, this is the overall comparisons. So, for generally unit cells, as I told already, we have given body centered cubic, face centered cubic and hexagonal close packed. So, here N is equal to the unit cell number is 2 for the BCC, 4 for the FCC and 6 for the HCP. What is the CN number over here for 8, 12 and 12? What is the A? That is the lattice parameter. For body centered cubic, it is 4 R by root over 3 and R is the radius of that particular atom. Face centered cubic, it is 2 R root over 2, and then for hexagonal close packed, it is 2 R. And what is the atomic packing factor number? So, for body centered cubic, it is 0.68, for face centered cubic, it is 0.74, and for HCP it is 0.74 also. Now, we are going to discuss about the closed packed crystal structures. So, in this the arrangement of the spheres are densely packed in order to take up the greatest amount of space available. So, very close, densely packed. These structures are found in two crystal structures, in hexagonal close packed structure and another one is in face centered cubic structure. So, for FCC generally the stacking sequences is like this: ABC and then ABC and then ABC. So, if you find that after ABC again the repeating cell is coming over here, that same thing has been written. The atomic alignment repeats every third plane. It is also called as cubic close packed structure also. When we are talking about the HCP, so hexagonal close packed, the stacking sequence is AB, AB, AB like that. So, it is a layer by layer structure. So, generally A, then after that B will come, then after that again A will come, then after that again B will come. So, this is the hexagonal close packed structure. Now, we are going to discuss about the polymorphism and allotropy. So, what is polymorphism? So, polymorphism is a phenomenon where some metals and non-metals have more than one crystal structure. I will give you the example so that you can better understand. So, if a material is an element solid, it is called the allotropy. So, what is the example of the allotropy? So, generally the best example is the carbon. It can exist as a graphite, as a diamond, as a amorphous carbon. So, it can be present into the environment in its so many forms. The prevailing crystal structure depend on both temperature and pressure. So, what is the allotropes of carbon generally? We can see graphene, we can see nanotube, we can see fullerene, we can see diamond and we can see the graphite. So, now let us discuss one by one about the carbon allotropes. So, first we are going to discuss about the graphene. So, what is graphene? It is described as one atom thick layer of the graphite, strongest thinnest material known to exist after diamond. Structure: generally two dimensional network of carbon atoms are there. Carbon atoms are bound within the plane by strong bond into a honeycomb array comprised of 6 membered rings. So, here you can see that 6 membered rings and it is forming one graphene atom. So, by stacking these layers on top of each other, one 3D graphite crystal is formed, basic building block for graphitic materials of all other dimensionalities. It can be wrapped into 0D, then we are calling it as a fullerene, rolled into 1D, we are calling it as a nanotubes, or stacked into 3D, that is the graphite. So, generally the graphene is 2D in nature. So, thus graphene is nothing but a single graphite layer. So, you can see that in this particular image there are stack of layers which is nothing but known as the graphite, and then a single layer, just we are calling it as a graphene. Now, what are the properties? Chemically most reactive form of carbon burns at very low temperature, generally 350 degree centigrade, high electrical conductivity, high thermal stability, high electron mobility at room temperature, high tensile strength. It is transparent and transmits about 98% of the light. So, that is why it is the latest materials, the whole researcher or maybe people are working on it, but still there are lots of things are still uncovered about the graphene. What are the application areas of the graphene? Generally there are n number of applications nowadays where we are using the graphene. So, in a brief idea, we are using it for the automobile industry, for the construction materials, for the aerospace industry, for lubricants, for the battery supercapacitor or maybe energy storage device, then flame retardant materials, then turbines, and then also for the biomedical applications like antimicrobial materials. Nowadays we are using for the scaffold, nowadays we are using for the orthopedic implants. So, there are n number of applications where we are using the graphene. So, what is graphite? So, graphite has a crystal structure distinctly different from that of diamond, more stable than diamond at ambient temperature and pressure. What is the graphite structure? Composed of layers of hexagonally arranged carbon atoms within the layers. Each carbon atom is bonded to 3 coplanar neighbor atoms by strong covalent bonds. Fourth bonding electron participates in a weak van der Waals type of bond between the layers. So, the electrical conductivity is relatively high in crystallographic directions parallel to the hexagonal sheets. So, here you can see the structure of the graphite. So, these all are the covalent bonds, and in between these the van der Waals bonds are working on it, and this is the carbon atoms. So, one layer by another layer is there is only the van der Waals bonds are working. What is the properties of graphite? Generally high strength and good chemical stability, high thermal conductivity, low coefficient of thermal expansions, high resistance to thermal shock, high adsorption of gases, and the good machinability, but there are so on. What is the use of graphite? As heating element for electric furnaces, as electrodes for arc welding, in metallurgical crucibles, in casting molds for metal alloys and ceramics, for high temperature refractories, etc. So, now we are going to discuss about the carbon nanotube. So, allotropes of the carbon with cylindrical nanostructure, long hollow structure with walls formed by one atom thick sheets of the carbon called the graphene. So, simple graphene 2D in structure. If we roll it, generally we are thinking that that is the carbon nanotube, also known as the Bucky tubes. They have length to diameter ratio of up to 132 into 10 to the power 6:1. They are members of fullerene structural family. Rolling up a graphene sheet may lead to a CNT. So, there are generally two types of carbon nanotubes. One is called the single walled carbon nanotubes, diameter is approximately to 1 nanometer. SWNT, the short form of single wall nanotubes, are wrapping with the layers of graphite which one atom thick layer called graphene into a seamless cylinder. They require catalyst for synthesis. So, from this image you can better understand. And when we are talking about the multi-wall carbon nanotubes, from the name itself you can understand that there are so many walls are present inside the carbon nanotubes. So, here they consist of multiple rolled layers, concentric tubes of the graphite. MWNTs have very complex structures and can be produced without catalyst. Purity of product is high. From this image you can get the essence of the multi-wall carbon nanotubes. Now, what are the properties and uses? Extremely strong, strip and relatively ductile materials, High strength to weight ratio helps in creating the lightweight spacecrafts. So, generally for the aerospace applications or maybe high temperature applications, space shuttles, we are using these carbon nanotubes. Easily penetrate membranes such as cell walls, helps in cancer treatment. So, that is why nowadays we are using it for the targeted drug delivery. Electrical resistance changes significantly when other molecules attach themselves to the carbon atoms to help in developing sensors that can detect the chemical vapors. So, that is why nowadays we are using it for the humidity sensors, biomolecule sensors, gas sensors and so on. Next, behave electrically as metal or maybe the semiconductor. So, that is why we are using it for the energy storage or maybe energy generations. So, what are the applications? It is we are using for the memory device, high end memory device, we are using it for the conductive composites, fuel cells, hydrogen storage, supercapacitor, microscopy, field emission display and the various so on. Now, we are going to discuss about the diamond. So, what is diamond? A metastable carbon molyphorm at room temperature and atmospheric pressure. Its crystal structure is a variant of zinc blend in which carbon atoms occupy the all positions, both zinc and the sulfur. Each carbon bonds to 4 other carbons and these bonds are totally covalent bonds over there. So, these all are the covalent bonds all. Relatively large diamond single crystals are used as gemstones, generally we are using it as an ornament. Industrially, diamonds are utilized to grind or cut other softer materials, yes, because it is the most hardest material till today. So, that is why generally the artificial diamonds we are using it for cutting any kind of hard materials. Physical properties of diamond make it an extremely attractive material. What are the physical properties? Hardest known material and has a very low electrical conductivity, this is number 1. Then has an unusually high thermal conductivity for a non-metallic material, number 2. Optically transparent in the visible and infrared regions of the electromagnetic spectrum, that is number 3. And last, has a high index of refraction, that is number 4. Now, we are going to discuss about the fullerene. So, fullerene first it was discovered in the year of 1985. It exists in discrete molecular form and consists of a hollow spherical cluster of 60 carbon atoms. So, that is why it is called the C60. So, generally it looks like a football. In the solid state, the units form a crystalline structure and packed together in a face centered cubic array. In pure crystalline form, it is electrically insulating. It can be made highly conductive and semiconductive by the additions of the impurities, by doping or maybe by some other means. So, it is the C60 structure, molecule structure, it is sometimes known as the Buckminster fullerene. Now, we are going to discuss about the temperature and pressure effect on allotropes of carbon. So, diamond is significantly denser than graphite. What is the atomic densities? So, generally that 1.14 into 10,231.14 into 10 to the power 23 per centimeter cube for graphite and 1.77 into 10,231.77 into 10 to the power 23 per centimeter cube for diamond. So, atomic densities for the diamond is too high. This suggests that the higher pressure would favor the formation of diamond. So, in this particular case, if we see this one, this side the temperature is increasing and this side the pressure, atmospheric pressure is increasing. So, diamond is at the top. So, that means it for preparations of the diamond you need a very high pressure. So, it varies from generally 10 to the power 3 to more than that. Then below that one is the graphite, and if you increase the temperature, so this is the vapor phase and this is the liquid phase. Indeed, as the following phase diagram shows, diamond is the most stable allotrope of solid carbon at high pressure. Temperature has little effect. As long as the pressure is high, diamond is favored over graphite at all temperatures up to the point of liquefaction. After that, the liquefaction will start. Now, we are going to discuss about the ceramic crystal structures. So, ceramics are compounds between metallic and non-metallic elements that we have already gone through. They have interatomic bonds either totally ionic or with covalent characteristics. Many ceramics have a combination of these two bonding types. So, you can see ionic bond as well as you can see the covalent bond. The degree of ionic character is being dependent on the electronegativities of the atoms. They are examples of inorganic materials like silicates, aluminates, oxides, carbides, borides and the hydroxides. So, what are the types of ceramic crystal structure? Generally we can find AX type crystal structure, AMXP type crystal structure and the last one is that AMBNXP type crystal structure. Now, we are going to discuss one by one. So, what is the characteristics of the component ions in crystalline materials? So, the crystal must be electrically neutral. It means all cations positive charge must be balanced by an equal number of anions negative charge, otherwise there will not be the neutrality. So, if RC by RA is less than 1, what is RC? RC is nothing but the radius of the cation. What is RA? RA is the radius of the anion. So, RC by RA if it is less than 1, then third one will be if RC by RA greater than 1, the coordination number is 12 and the number 4 is that the most common coordination numbers for ceramic materials are 4, 6 and 8. So, if you see in this particular case, so coordination numbers and geometries for the various cation anion radius factor RC by RA. So, coordination number if it is 2, the cation anion radius ratio is less than is equal to 0.155. So, you can see from this particular image. If we are talking about 4, so if we see the 4, it varies from 0.225 to 0.414 and from this image you can get the picture. And then if we talk about the 8, so it is varies from 0.732 to 1. So, what is the coordination geometry? The coordination geometry looks like this. Now, what is the stable ceramic crystal structures? So, generally as I told already, so it should be balanced the cations and anions. So, in this particular case this is the cations and it is surrounded by the 4 anions, it is stable. In this particular case also it is very stable, but in this particular case it is unstable because there is some vacant positions in between that. Now, we are going to discuss about the AX type crystal structure. So, AX type compounds are those in which there are equal number of cations and anions, this is the vital one. So, equal number of cations and anions. In AX, A denotes cation and X denotes anions. So, example of AX type crystal structure materials rock salt or maybe the sodium chloride, cesium chloride structures, zinc blende structures. So, these all are the examples for AX type crystal structure. What is rock salt structure? Most common AX structure is sodium chloride or maybe the rock salt type. So, coordination number for both cations and anion is 6, it is totally balanced. Cation anion ratio is between 0.414 and 0.732. Unit cell is generated from an FCC arrangement of anions with one cation situated at the cube center and one at center of each of 12 cube edges. So, from this particular image you can understand that here chlorine is there, then after that here the chlorine is there, then after that two sides is the sodium, then here it has been changed totally, then again it has been changed. So, it is that is why it is called the AX type crystal structure. So, here all the cations and anions numbers are balanced. So, what are the examples? Sodium chloride, magnesium oxide, manganese sulphide, lithium fluoride and the iron oxide. Now, we can give the examples of the cesium chloride structure. So, coordination number for both ions is 8, it is balanced. Anions are located at each of the corner of the cube, here all are anions are present and only in the cube center the cations is present. Interchange of anions with cations produces the same crystal structure. So, if we change it, it is not a BCC structure because ions of two different kinds are involved. Then we are going to discuss about the zinc blende structure or maybe in technical term we are calling it as a sphalerite. So, coordination number is 4, and all ions are tetrahedrally coordinated. All corner and face positions of cubic shell are occupied by S atoms, while for zinc atoms fill interior tetrahedral positions. So, this green in color are the zinc atoms and the yellow in color are the sulfur atoms. Each zinc atom is bonded to 4 sulfur atoms. Atomic bonding is highly covalent. What is the examples? Zinc sulfide, zinc tellurium and silicon carbide. Now, we are going to discuss about the AMXP type crystal structure. So, if the charges on the cations and anions are not the same, a compound can exist with the chemical formula AMXP, where M and P not is equal to 1. So, for example, CaF2, which is known as the fluoride, coordination number of cation Ca2 plus is 8 and anion F minus is 4. Here it is not balanced. Anion F minus packing is simple cubic over here. So, this blue in color all are the Ca atoms and F are the F minus or maybe the fluoride anions. So, calcium ions are positioned at centers of cubes with fluorine ions at corners. Ionic ready ratio is Rc by Ra for calcium fluoride CaF2 is about 0.8. Other examples like zirconium oxide, uranium oxide, plutonium oxide or maybe the thorium oxides. Now, we are going to discuss about the AX, B and XP type crystal structure. So, it is also possible for ceramic compounds to have more than one type of cations. So, here generally 2 types of cations are present. So, for 2 types of cations represented by A and B, their chemical formula may be designated as AM, BN, XP. So, for example, BaTiO3 barium titanate. So, in this particular case what happened? BaTiO3 having 2 cations Ba and Ti. So, Ti is green in color and all the blue are the Ba, and here O2 minus is acting as a anion over here. So, anion O2 minus packing in FCC, Ba2 plus ions are situated at all 8 corners of the cube and a single Ti4 plus is at the cube center. You can see from this particular image with O2 minus ions located at the center of each of the 6 faces. It is cubic above 120 degree centigrade temperature. So, now some common ceramic crystal structure examples. So, like rock salt structure type is AX, at anion packing is FCC. Here the cation number is 6, anion is 6. Examples sodium chloride, FeO, MgO like that. Cesium chloride, so generally CsCl. So, here it is simple cubic, cation and anion number is also equal. For zinc blend also it is equal, zinc sulfide and silicon carbide. For fluoride generally it is AX2 type structure type. Here the cation number is 8 and the anion number is 4. So, CaF2 or UO2 or maybe THO2. Generally we are talking about the peroxide materials. Nowadays it has been widely used for the solar cells. So, the generally the structure type is ABX3 or FCC in structure. So, it is 12A and the 6B because 2 cations are present in this particular case. So, anion is 6 like BaTiO3, SrZrO3, SrSnO3 like this. If we are talking about the spinel, generally the crystal structure type is AB2X4, FCC in structure. Here also 2 cations are present 4A and 6B and anions number are 4. So, examples is magnesium aluminate or maybe FeAl2O4. Now, we are going to discuss about the silicate ceramics. So, generally it is composed mainly of silicon and oxygen, two most abundant element on earth's crust. So, generally it is having basic building block. So, tetrahedron SiO4 4 minus. So, SiO bonding is largely covalent but overall block has charge -4. Various silicate structure arises from different ways in which SiO4 4 minus units are combined into 1, 2, 3D arrangement as silica, silica glasses, the silicates. So, what is the classification of silicates? Generally bulk of soils, rocks, clays and the sands. So, generally this type of silicates we are seeing day to day life. What is silica? Chemically the simple silicate material is silicon dioxide or maybe the silica or SiO2. Structurally it is 3-dimensional network generated when every corner oxygen atom is each SiO4 minus tetrahedron is shared by the adjacent tetrahedron. So, from this image you can see this one. It is electrically neutral and ratio of silicon to oxygen atom is 1:2. 3 primary polymorphic crystalline forms of silica generally we are seeing, that is quartz, then cristobalite and the tridymite. Then another types is silica glasses, non-crystalline solid or glass called fused silica or maybe the vitreous silica. So, other oxides like B2O3 and GeO2, germanium oxide also form glassy structure as well as SiO2, silicon dioxide terms at the network formers. Other oxides such as titanium dioxide TiO2, L2O3 while not network formers substitute for silicon and become part of and stabilized network called as intermediates. Common inorganic glasses are silica glasses with added other oxides like calcium oxide CaO or maybe the sodium oxide Na2O. These oxides do not form polyhedral network, rather modify SiO4 4- network called as network modifiers. Then we are going to discuss about the silicates. So, frameworks based on the linkage of SiO4 4- tetrahedra, 1, 2, 3 of corner oxygen atoms of the SiO4 4- tetrahedron are shared by other tetrahedra to form the complex structures. Types of the silicates: simple silicates, simple ones involved isolated tetrahedra. What are the example? So, phosphorite Mg2SiO4 has equivalent of 2 Mg2 plus ion associated with each tetrahedron such that every Mg2 plus ion has 6 oxygen nearest neighbors. Then acarmenite Ca2 Mg Si2O7 has equivalent of 2 Ca2 plus ions and 1 Mg2 plus ion bonded to each Si2O7 6-. What is layered silicate? It is 2-dimensional sheet or the layered structures. From the name itself we can understand. Basic structure is the characteristics of the clay and other minerals produced by sharing of 3 oxygen atoms in each of the tetrahedra, represented at Si2O5 whole 2. Common clay mineral kaolinite, talc or maybe the mica. Then we are going to discuss about the polymer structures. What about the polymer crystallinity? So, crystallinity is the indication of amount of crystalline region in polymer with respect to amorphous content. Polymer crystallinity is the packing of molecular chains to produce an ordered atomic array. As crystallinity is increased in polymer, generally the density decreases, stiffness, strength and toughness increases, heat resistance property increases, polymer are stronger and more resistance to dissolutions and softening by the heat. What is degree of crystallinity for the polymer? It ranges from completely amorphous to crystalline. Density of crystalline polymer will be greater than an amorphous one of same material and molecular weight. Degree of crystallinity by weight can be determined from accurate density measurement. What is that? Percentage crystallinity is equal to rho C into rho S minus rho A by rho S into rho C minus rho A whole into 100, because we are calculating the percentage over there, where rho is the density of the specimen, rho is the density of totally amorphous polymer, rho C is the density of perfect crystalline polymer. So, generally degree of crystallinity of polymer depends on rate of cooling during solidifications and on chain configuration. What is the polymer crystals? Semi-crystalline polymer consists of small crystalline regions, generally it is known as the crystallites. Polymer crystals are regularly shaped thin platelets or lamellae 10 to 20 nanometer thick platelets from a multilayered structure. What is chain folded model? The molecular chains within each platelet fold back and forth on themselves with folds occurring at the faces itself. So, you can see that it has been folded at the faces over there. Each platelet will consist of number of polymer molecules. So, generally the thickness is around 10 nanometer. Bulk polymers that are crystallized form a melt are semi-crystalline and form the spherulite structure. What is spherulite? Aggregate of ribbon like chain folded crystallites. So, you can see from this particular image. So, interspherulitic boundary and these all are the spherulitic structure. Generally 10 nanometer thick that radiate outward from a single nucleation site in the center. They have fast growth and forms lamellar structures. Polyethylene, PVC, PTFE and nylons form a spherulitic structures when they crystallized from a melt. Now, we have come to the last. So, just we have to summarize the whole lecture. So, in this particular lecture we have discussed about the different crystal structures like metallic, ceramic and the polymers. Then we have discussed about some metallic crystal structure that is like BCC, FCC and the HCP. We have discussed about the coordination number and the atomic packing factor in for the FCC and for the HCP crystals also. Ceramic crystal structures are based on charge neutrality and cation anion ready ratios that we have already discussed. We have discussed about the interatomic bonding in ceramics is ionic or maybe the covalent or maybe the both. In polymer structures, polymer crystallinity provides the informations about crystalline region in the polymer itself. Thank you.